Look up at the night sky, a tapestry woven with countless stars. Each one, a distant beacon, holds a secret far profounder than mere light. These celestial bodies are not just points of beauty. They are the universe's ultimate foundries, cosmic engines tirelessly forging the very elements that constitute everything around us, including ourselves. From the simplest hydrogen to the most complex gold, every atom originating beyond the Big Bang itself has a stellar birthplace. This journey, from diffuse gas to dense matter and ultimately into the building blocks of planets and life, is a testament to the universe's incredible transformative power. We are quite literally stardust. The calcium in our bones, the iron in our blood, the oxygen we breathe, all were once locked within the fiery hearts of ancient, long-dead stars. Understanding this cosmic alchemy unlocks the fundamental story of our existence and the universe itself. This documentary will embark on a journey deep into these stellar factories, unveiling the processes that transmute one element into another under conditions of extreme heat and pressure. We'll explore the life cycles of stars, from their birthplaces in nebulae to their dramatic conclusions. From the proton-proton chain transforming hydrogen into helium within our own sun, to the violent supernovae that scatter heavy elements across galaxies, we'll witness the cosmic dance of creation. Prepare to unravel the secrets of the elements and their stellar origins. Our story begins not with a star, but with the universe itself. Approximately 13.8 billion years ago, the cosmos, as we know it, emerged from an infinitely hot, dense state in an event scientists call the Big Bang. This moment defined the earliest elemental landscape. In the first few minutes after the Big Bang, the universe was hot enough for nuclear fusion to occur. This primordial nucleosynthesis created the lightest elements: hydrogen, helium, and trace amounts of lithium. These were the only building blocks available. Roughly 75% of this early universe by mass was hydrogen, mainly individual protons, while nearly 25% was helium, formed from 2 protons and 2 neutrons. Lithium made up only a minuscule fraction, less than 1/10,000%. Crucially, no elements heavier than lithium were created during the Big Bang. The universe simply expanded and cooled too rapidly for further fusion to occur. Carbon, oxygen, iron, and all the elements essential for planets and life were entirely absent. This posed a profound problem. Without heavier elements, how did the cosmos evolve into the rich, diverse tapestry we observe today? The answer lies in the next chapter of cosmic evolution, the formation of the very first stars. Massive clumps of this primordial hydrogen and helium gas began to coalesce under gravity's relentless pull. Over millions of years, these diffuse clouds grew denser and hotter until conditions were ripe for an extraordinary transformation. This process, known as gravitational collapse, is the fundamental mechanism behind star formation. It takes vast quantities of matter and compresses them to extraordinary densities, a critical step towards igniting the universe's first internal furnaces. As these gas clouds contracted, the pressure and temperature at their cores steadily increased. Atoms collided with greater frequency and force, building immense thermal energy. This escalating heat signaled the approach of a momentous event. Eventually, the core reached a critical temperature, measured in millions of degrees Celsius. This was the ignition point, where the incredible gravitational squeeze finally overcame the electrostatic repulsion between atomic nuclei. At this threshold, a star was truly born. Nuclear fusion commenced, converting hydrogen into helium and releasing an enormous amount of energy. The universe, once dark save for the afterglow of its birth, now had self-luminous beacons. Stars don't just appear fully formed. They emerge from vast reservoirs of gas and dust called nebulae. These nebulae are stellar nurseries, regions where the interstellar medium is dense enough for gravitational forces to overcome thermal pressure. Within these nebulae, slight density fluctuations exist. Perhaps a shockwave from a nearby supernova or the passage of a spiral arm in a galaxy can trigger further collapse in these already denser regions, initiating the star formation process. As a dense core begins to shrink, it forms what is known as a protostar. This embryonic star is not yet hot enough for sustained nuclear fusion, but continues to gather mass from the surrounding cloud, growing steadily. The protostar's gravity continues to pull in more material, and as this gas falls inward, its gravitational potential energy is converted into kinetic energy, then into thermal energy. This heats the protostar's core considerably. This prestellar phase can last for hundreds of thousands to several million years, depending on the star's eventual mass. During this time, the protostar radiates energy primarily from the heat generated by its contraction. Eventually, the core temperature of the protostar reaches a critical threshold, approximately 10 million degrees Celsius. At this immense heat, the kinetic energy of hydrogen nuclei is sufficient to overcome their natural electrostatic repulsion. This marks the beginning of sustained nuclear fusion. Hydrogen atoms fuse to form helium, releasing a tremendous burst of energy. This outward pressure generated by fusion precisely counteracts the inward pull of gravity. The star has now achieved hydrostatic equilibrium, a stable balance between gravity and internal pressure. It finds its place on the main sequence, where it will spend the vast majority of its active life. Our Sun is currently in this phase. The main sequence is where stars truly begin their work as cosmic forges, diligently converting hydrogen into helium. The primary process for stars like our Sun is called the proton-proton chain reaction. In this chain, 4 individual hydrogen nuclei, which are simply protons, are gradually fused together through a series of steps to form a single helium nucleus. Each step releases energy in the form of gamma rays, positrons, and neutrinos. For more massive stars, those significantly larger than our Sun, another process dominates, the CNO cycle. This stands for carbon-nitrogen-oxygen cycle and uses these heavier elements as catalysts to fuse hydrogen into helium. While carbon, nitrogen, and oxygen are not consumed in the CNO cycle, acting merely as intermediaries, their presence dramatically accelerates the rate of hydrogen fusion compared to the proton-proton chain. The CNO cycle is highly temperature-sensitive. Its efficiency increases significantly with even small rises in core temperature, making it the dominant fusion mechanism in hot, massive stars where the core temperatures greatly exceed that of the Sun. The main sequence phase is the longest stage in a star's life, lasting billions of years for Sun-like stars and much shorter periods, only millions of years, for the most massive ones. This duration is dictated entirely by their mass. During this extended period, stars remain stable, continuously converting hydrogen into helium in their cores. This continuous fusion is the foundational act of cosmic element creation, producing the first new elements since the Big Bang. Eventually, even the most prodigious furnaces run out of their primary fuel. For a main sequence star, this means its core's hydrogen supply dwindles. This marks the beginning of the end of its stable existence. As hydrogen fusion in the core slows, the outward pressure weakens. Gravity, ever present, begins to gain the upper hand, causing the star's core to contract and heat up even further. This contraction, ironically, heats a shell of hydrogen around the dying core. Here, hydrogen fusion reignites with renewed vigor due to the intense temperature and pressure from the contracting core. The energy from this shell fusion is so immense that it far outweighs the previous core fusion. This tremendous outward pressure causes the star's outer layers to expand dramatically, cooling as they do so. The star transforms into a red giant. Its vastly increased surface area means its light is spread thinly, giving it a cooler, redder appearance. This is the fate awaiting our Sun in about 5 billion years. As the red giant's core continues to contract, reaching even higher critical temperatures, around 100 million degrees Celsius, helium fusion commences. This is known as the triple-alpha process. In the triple-alpha process, three helium nuclei, also known as alpha particles, fuse together directly to form a single nucleus of carbon. This marks the first direct creation of a heavier element beyond helium within a core. These carbon and oxygen atoms accumulate in the star's core, becoming the new ash. For Sun-like stars, this will be the heaviest elements they ever produce. Their internal furnaces simply aren't powerful enough for further fusion. Beyond the helium-fusing core, a shell of hydrogen continues to burn, enveloping the star. This complex layered structure creates a turbulent and active interior for the red giant. The instability of these different burning shells can cause the star to pulsate, periodically expanding and contracting. This leads to variations in the star's luminosity and size, particularly for stars on the asymptotic giant branch. As the red giant exhausts its helium fuel, the carbon and oxygen-rich core once again begins to contract. This time, fusion completely ceases in the core. The star swells to enormous proportions. The outer layers become extended and tenuous, eventually creating conditions for their expulsion into space, a critical step for enriching the galaxy with new elements. These expelled outer layers form a beautiful, expanding shell of gas known as a planetary nebula. This process provides a gentle return of elements like carbon and oxygen back into the interstellar medium. At the heart of the planetary nebula lies the remnant of the star's core, a white dwarf. This incredibly dense, hot, and small object is composed almost entirely of electron-degenerate carbon and oxygen. While Sun-like stars gently exhale their elements, massive stars, those born with more than 8 times the Sun's mass, follow a far more dramatic and powerful evolutionary path. Their life cycles are brief but extraordinarily energetic. Their immense gravity means their cores reach far higher temperatures and pressures than smaller stars. This allows them to fuse progressively heavier elements in their cores beyond carbon and oxygen. After hydrogen fusion ceases, the core contracts and heats, igniting helium fusion in the core and hydrogen fusion in a surrounding shell, similar to a red giant. But for massive stars, this is just the beginning. Once helium is exhausted, the core contracts further, reaching temperatures of around 600 million degrees Celsius. This allows carbon fusion to begin, forming elements like neon, sodium, and magnesium. This process continues in stages, with each successive fusion reaction requiring higher temperatures and pressures. After carbon, oxygen fusion ignites, forming silicon and sulfur at over 1 billion degrees Celsius. Finally, around 2 to 3 billion degrees Celsius, silicon fusion begins, rapidly creating elements close to iron on the periodic table: phosphorus, sulfur, chlorine, argon, potassium, calcium, scandium, titanium, vanadium, chromium, manganese, cobalt, and nickel. These elements form in a layered structure within the star, much like an onion. The outermost shell fuses hydrogen, then helium, then carbon, and so on, down to the innermost core, which is composed almost entirely of iron and nickel. Each stage of fusion produces less energy per reaction than the previous one, and the star burns through its fuel more quickly. The final silicon burning phase lasts mere days for a star that has lived millions of years. The culmination of this stellar nucleosynthesis is the creation of iron. Iron 56, specifically, is a uniquely stable atomic nucleus. It represents a crucial turning point in a star's life. Fusing elements lighter than iron releases energy. This energy provides the outward pressure that supports the star against its crushing gravity. But fusing iron, or elements heavier than it, actually consumes energy. Once a massive star's core is predominantly iron, the stellar furnace reaches an impasse. There is no longer a viable nuclear reaction to generate the outward pressure needed to counteract the immense gravitational force. Without a source of internal heat and pressure, gravity finally wins. The iron core collapses catastrophically inward on itself in a fraction of a second. This is the moment of unavoidable catastrophe for the star. The speed of this collapse is astonishing. The core shrinks from a diameter comparable to Earth's to just tens of kilometers in milliseconds. This rapid implosion generates an immense shockwave. When the collapsing core reaches nuclear densities, it essentially bounces off the incompressible stellar material. This rebound creates an outward-moving shockwave, powerful enough to destroy the star. This cataclysmic event is a Type II supernova. For a brief period, the exploding star outshines an entire galaxy, scattering its highly enriched material, forged over millions of years, across vast cosmic distances. Supernovae are nature's ultimate fireworks, but they are far more than just brilliant displays. They are the primary cosmic factories for all elements heavier than iron, including many essential for life. The extreme conditions within the collapsing core and the subsequent explosion create an environment unparalleled in the universe for forging new elements. One key process is the rapid neutron capture process, or R process. During the R process, atomic nuclei rapidly absorb a large number of neutrons before they can undergo radioactive decay. This builds up very heavy, unstable isotopes of elements. These highly neutron-rich nuclei then undergo a series of beta decays, where a neutron transforms into a proton, emitting an electron. This increases the atomic number of the element, forming progressively heavier elements. Elements like gold, platinum, and uranium, which are vital for technology and have immense cultural value, owe their existence to these rare and violent supernova explosions. Beyond the R process, the intense energy of the supernova shockwave itself can strip away electrons from atoms and break apart some existing nuclei, leading to various sporulation reactions that also produce new elements. The supernova explosion also disperses the elements forged throughout the star's prolonged life: the hydrogen, helium, carbon, oxygen, neon, magnesium, silicon, and iron, into the interstellar medium. This cosmic enrichment is crucial. It means that subsequent generations of stars and planetary systems will form from material that is far more diverse and rich in heavy elements than the universe's primordial soup. Without supernovae, the universe would be a much simpler place, perhaps containing only hydrogen, helium, and small amounts of lithium, carbon, and oxygen. The very existence of rocky planets and life would be impossible. But elements produced by collapsing massive stars are not the only contributors to the galactic chemical enrichment. Lower to medium-mass stars also play a vital, albeit gentler, role. After their red giant phase, Sun-like stars that fuse helium into carbon and oxygen in their cores reach a point where nuclear fusion ceases entirely. Their outer layers become increasingly unstable. Thermal pulses from the helium-fusing shell below cause the star to expand and contract violently. During these pulses, the star sheds its outer layers in a series of gentle but powerful outflows. These expelled shells of gas and dust form a captivating structure known as a planetary nebula. Despite their name, they have nothing to do with planets. The term arose because early telescopes made them appear planet-like. Within these nebulae, elements like carbon, nitrogen, oxygen, and even some heavier ones formed through slow neutron capture process during the red giant phase are gently puffed into space. The process of slow neutron capture, or process, occurs in stars like red giants. Here, neutrons are captured slowly by atomic nuclei, allowing time for radioactive decay before another neutron is captured. This process creates about half of the elements heavier than iron, including elements like barium, strontium, and technetium. While not as dramatic as supernovae, these stars are vital for cosmic enrichment. At the heart of a planetary nebula, what remains is an incredibly dense, extremely hot, and very small stellar core, a white dwarf. It's the inert remnant of a meteor-mass star. A white dwarf no longer undergoes nuclear fusion. It slowly cools over billions of years, radiating its residual heat into space, eventually becoming a cold, dark black dwarf, a theoretical end state not yet observed. The material expelled by planetary nebulae, along with the more violent supernova remnants, constitutes the recycled raw material for the next generation of stars. This cosmic cycle is continuous. Over cosmic time, the interstellar medium gradually becomes more enriched with heavier elements. This increasing metallicity of the gas clouds significantly influences where and how new stars form. Consider our own Sun, a second or even third-generation star. It formed from a cloud of gas and dust that already contained a rich assortment of elements, courtesy of countless previous stellar life cycles and deaths. This pre-enrichment was absolutely critical for the formation of rocky planets like Earth. Without iron, silicon, oxygen, magnesium, and other elements forged in ancient stars, there could be no solid ground beneath our feet. The Earth itself is a cosmic junkyard, a collection of atoms synthesized in various stars over billions of years. Its very existence is a testament to the universe's ongoing cycle of creation and destruction. The iron in our planet's core, which creates its protective magnetic field, was forged in spectacular, short-lived, massive stars. That superhot element eventually cooled to become the dense heart of our world. The silicon and oxygen that make up most of Earth's crust and mantle were produced by a wider range of stars, from sun-like stars shedding their outer layers to massive stars ending in supernovae. The water that flows in our oceans and sustains life is composed of oxygen, primarily created in the cores of stars, combined with hydrogen from the Big Bang, a cosmic partnership across epochs. Even the trace elements crucial for biological processes, such as iodine for thyroid function or selenium for enzymes, have their unique stellar tails, often forged in the most extreme cosmic events. The formation of a solar system capable of supporting life is a grand cosmic lottery dependent on the availability of these heavier elements. It requires the right ingredients at the right time in the right place. The very existence of life on Earth is inextricably linked to the life cycle of stars. We are living proof that the universe is capable of self-enrichment, of building complexity from its primordial simplicity. From the initial Big Bang nucleosynthesis, which gave us hydrogen and helium, to the ongoing stellar fusion and explosive supernovae, the universe has patiently assembled the elemental blueprint for everything. The story of the elements is a continuous saga, still unfolding. Stars are still being born, still fusing hydrogen, still evolving, and still dying, scattering their inner workings across the cosmos. Galaxies themselves are immense ecosystems where this cosmic recycling occurs on a grand scale. Gas and dust are drawn into spiral arms, compressed, fostering new star birth, and then enriched by stellar deaths. Each new generation of stars is born from materials slightly more metallic than the last. This means the universe is slowly but surely creating more opportunities for rocky planet and potentially life formation. The study of stellar nucleosynthesis is not just astrophysics, it's cosmochemistry, cosmobiology, and ultimately our origin story. It helps us understand where we came from and what we are truly made of. Every breath we take, every cell in our body, every grain of sand, and every mountain range whispers tales of collapsing gas clouds, fiery stellar cores, and violent cosmic explosions. The universe is not just expanding, it's evolving, chemically transforming itself year after year, star by star. We are living in a cosmos that is dynamically building new things, fueled by the very stars we gaze upon. Consider the sheer scale. Our Sun alone converts about 600 million tons of hydrogen into 596 million tons of helium every second. That missing 4 million tons is the energy that powers life on Earth. Think of the vast cosmic distances these elements travel. Forged in one star, scattered in another, then gravitationally drawn into a new nebula, only to coalesce into a new star and its planetary system. The gold in our jewelry, the iron in our tools, the silicon in our computers, all testify to a universe that is both violent and incredibly creative, repurposing elemental ingredients over eons. The elemental composition of stars also influences their ultimate fate. More massive, metal-rich stars behave differently than primordial, metal-poor stars, influencing which elements they produce and how they die. Advanced technologies, like spectroscopy, allow astronomers to decipher the elemental fingerprints of distant stars and gas clouds. By analyzing their light, we can determine their chemical makeup, revealing their origins. Each atom, with its unique set of electron shells, emits and absorbs light at specific wavelengths, creating a unique spectral barcode. This allows scientists to map the distribution of elements across the cosmos. This cosmic census of elements helps us piece together the universe's chemical evolution, revealing how the abundance of different elements has changed over billions of years, providing strong evidence for nucleosynthesis. The heavier elements that enable biochemistry, for instance, were not immediately available after the Big Bang. It took generations of stars to produce sufficient quantities for planets and life to emerge. This means that early galaxies would have been stellar nurseries primarily for hydrogen and helium stars, with little possibility for rocky planets or complex chemistry. Our universe truly matured over time. As we delve deeper into the universe, with powerful new telescopes like the James Webb Space Telescope, we are observing galaxies further back in time, witnessing this evolutionary process firsthand. JWST reveals the earliest stars and galaxies, showing us their elemental composition. It's a cosmic archaeological dig, unveiling the building blocks of the universe as they first began to accumulate. These observations continue to confirm the predictions of stellar nucleosynthesis, providing empirical evidence for the fiery factories within stars. The theory holds strong. The elements of life, carbon, hydrogen, nitrogen, oxygen, phosphorus, sulfur, are nicknamed CHNOPS. They are the most abundant elements in living organisms and all have profound stellar connections. Carbon, forming the backbones of organic molecules, is primarily a product of helium fusion in red giant stars. Without this stage, life as we know it would be impossible. Oxygen, crucial for respiration and water, is forged in both red giants and massive stars. Its abundance is a testament to the sheer number of stars that have lived and died throughout cosmic history. Nitrogen, a key component of proteins and DNA, is primarily formed via the CNO cycle in massive stars and also through this process in lower-mass red giants. Its journey to life on Earth is complex. Phosphorus and sulfur, integral to energy transfer and protein structure, are forged in the more violent environments of massive stars and supernovae. Their presence marks the universe's capacity for complexity. We are born from fire. The warmth of our bodies, the energy that fuels our cells, is ultimately derived from the sunlight, itself a product of hydrogen fusion in our sun, and ultimately from the processes that built its very atoms. This profound connection between stars and life transcends mere scientific fact. It imbues our existence with a cosmic grandeur. We are not separate from the universe, we are an expression of its deepest workings. The relentless cycle of stellar birth, life, and death has woven the fabric of reality. It is a testament to the universe's incredible chemical evolution and its capacity to produce ever-increasing complexity. From the nascent hydrogen and helium after the Big Bang to the vibrant diversity of the periodic table today, stars have been the cosmic alchemists, tirelessly transforming matter and energy. The Big Bang created the canvas, but stars provided the rich palette of colors and textures, enabling the universe to paint its masterpieces: planets, galaxies, and ultimately, life itself. Every element has a story, a journey through cosmic fire and pressure. Learning these stories illuminates not just the cosmos, but our place within it as children of the stars. So the next time you look up at the infinite expanse of the night sky, remember that you are gazing upon the very furnaces that built you. You are stardust made manifest, connected to the deepest cosmic processes.